Y'all doing tonight? Guys, we're streaming this, and that was embarrassing. How are you all doing tonight? There we go. Welcome to Astronomy on Tap. There is a great crowd here tonight. How many of you are first-timers at Astronomy on Tap? Oh, wow, welcome. All right. Well, that's perfect. We're going to give you a little intro into what is Astronomy on Tap. And then we will talk a little bit about the agenda we have tonight. We have two fantastic talks waiting for you tonight. So we'll go ahead and...
Pretty happy to see so many of you tonight.
Yeah.
Awesome.
So...
that might be the last of the year, so that's
So we'll start by introducing ourselves. My name is Tracy Becker.
I'm Michael Velez.
I'm Aaron Dillon. I'm Vincent Hugh.
Well,
We have a speaker tonight also who's part of the team. So we have with him on and Brian Begg, who's actually not here tonight.
okay.
So what is astronomy on tap, Michael? You want the microphone?
Yes. Thank you. All right. What is Astronomy on Tap? Well, Astronomy on Tap is a global phenomenon. It's basically we all come together and enjoy an astronomy talk or multiple astronomy talks amongst beer or soda, your choice. But as you can see on the map, yes, it happens all over the world, which is really special. And I love that we are spreading the word of astronomy to everybody. And right here in San Antonio, we are fun. Because you can win great prizes and treasures. We always have a good time. At the end of our of the talks, we will have trivia. If you all stay, there will be some cool prizes up here, some stickers, and this really cool photo, top prize. So you can take that home with you, and including an astronomy-themed card game. So if you want to be a nerd while playing a game, win the prize. And of course, probably the best thing, you interact with world-class scientists right here in San Antonio. Yes. Woo! All right. Aaron?
Yeah, so today we got some great talks lined up for you all. We have first up Sam Hart, who will be giving a talk on a modern-day doomsday scenario based on some solar storms. And then we will have a Q&A after each talk, and then a break after the Q&As. Go to the bathroom, get some more drinks. Then we have Astronomy in the News. Our own Caleb DeMar will pronounce the Astronomy in the News for a little bit. After that, we'll have the second talk by Dr. Vincent and about Jupiter's light show when moons create auroras, and also a Q&A. And then after the Q&A, we have trivia, as Mike was just talking about, with our wonderful prizes.
Also, if at any point you all have questions about any of the presentation material, text your questions to this number here, and we will ask them during the Q&A section. And also throughout the night, you can tweet or Instagram your thoughts or photos. Hashtag AOTSATX. Don't forget the hashtag. Oops. What? Yes. Here we go. So tonight's first speaker is Sam Hart. Round of applause. Yeah, where'd it go? Here we go. Sam is a late-stage graduate student at the University of Texas in San Antonio in the joint program with the Southwest Research Institute. His primary research topic is heliophysics, meaning he studies how the sun influences the rest of the solar system, including our own Earth. Though he finds his research interesting, he is especially fascinated by the stories told and adventures embarked by those who studied the sun before him. This presentation details one such event where the sun displayed its unparalleled might to the citizens of Earth and foreshadowed the collapse of modern civilization's electronic infrastructure. Sam will read his first-hand accounts of those who bore witness, not his first-hand account, Yeah, there's some good makeup you use. Bore witness to the great solar system of 1859, and he will discuss the catastrophic consequences should such an event happen today. Ladies and gentlemen, please welcome Sam Hart. Before we start, also, let me mention, for those of you who have been here before, you know what's about to come. For those of you that are new, we have a drinking word. When Sam says his drinking word, we are all going to say, "Woo!" Hold up our drink and take a sip. Yeah. Don't forget to take a sip. Yeah. Don't leave it up. Tonight's drinking word for Sam is storm. All right, let's practice.
Storm.
I like it. All right, here we go.
Oh. Hot. Okay, and then back, and then what's the laser pointer? There we go. Okay. Thank you, Michael, for the kind introduction. Hello, everybody. Hi. Today, I'm going to be talking about the Great Solar Storm of 1859. On a particular day this year, sorry, I'm a little nervous, sheepish. On a particular day this year of 1859, a piece of the sun erupted into space and was headed straight for Earth. And we noticed a bit of strange phenomena happening on Earth, and we will discuss what that is. And then we are going to talk about what would happen if such an event happened today. And based on my title, the answer is not good. But before we get to today, let's go back to 1859 with the man who observed this event, Richard Christopher Carrington. Richard was born in 1826 in England. His father, perhaps coincidentally, perhaps not, owned a brewery. And from a young age, Richard was destined for the church, mostly at the will of his father. But he always had a propensity for math and science. And when he went to university, he took an astronomy course, and he fell in love. So he went home, and he told his father that he didn't want to join the church. He wanted to be an astronomer. And by all accounts, his father did not oppose, and thus Richard's astronomy career was born. However, it didn't start off all that great. He bounced around from observatory to observatory, and he always had some problems which caused him to leave. So instead of going to another observatory, he decided to build his own, called the Red Hill Observatory. And I think this observatory is every astronomer's dream. Here are his living quarters off on the left, and in the nice countryside of England. And connected to his house is his observing dome. So he would wake up and go to work. Once he built his observatory, his astronomy career really began to take off. He became a member of the Royal Astronomical Society. Other famous people in that society include Isaac Newton, if my memory serves me correctly. He started doing nighttime astronomy, cataloging circumpolar stars. For those who don't know, a circumpolar star is a star that never sets. And a famous example of a circumpolar constellation is the Big Dipper. We see it all the time because it's always out. But he decided that the night shift wasn't for him, and he would start to observe the sun. He would make detailed observations of sunspots. Shown here is an individual sunspot. Sunspot groups, which is the whole collective of sunspots. And with these observations, he would study how the sun rotates. That is a topic for another talk. So he did this for several years until September 1st, 1859. And something very strange happened, and instead of me telling you about it, I will instead read Richard Carrington's own words. He says, "While engaged in the forenoon of Thursday, September 1st, in taking my customary observation of the forms and positions of the sunspots, an appearance was witnessed which I believe to be exceedingly rare." How right you are, Richard. He continues. Pause. Within the area of the Great North Sunspot Group, 2 patches of intensely bright and white light broke out. My first impression was that by some chance, a ray of light had penetrated a hole in the screen, for the brilliancy was fully equal to that of direct sunlight. So for further explanation, we have to go into Richard Carrington's observation methods, seen here on the left. So to observe the sun, he had a telescope here, and the telescope was pointed at the sun, and the telescope would then focus the light onto a glass film. And this glass film was right where he would sit down, and he would draw nice pictures and take notes of what he was observing. But for anyone here who has observed the sun in the day knows that you can't just point a telescope at the sun. If you look through that telescope, you will go blind immediately. And even if you don't look through the telescope itself can melt. When you focus the sunlight, it gets very hot and your lenses can melt. So we use what is called a solar filter, which is this doohickey right in the front of the telescope there. And all a solar filter does is reflect most of the light coming in and lets just a little bit of light through so that you can get detailed observations of the sun without ruining your equipment or your eyes. So when he says, "I thought there was a hole in my screen," he thought that his solar filter had broken and that all of the sunlight was coming through the telescope instead of just a fraction of it. And although he didn't take like a live photo, I assume this is kind of what he saw with this magnifying glass here, just a bright, intense light on the sun. So, upon learning that it wasn't a crack in the screen, Richard Carrington says, "I hastily ran to call someone to witness the exhibition with me, and on returning within 60 seconds was mortified to find that the last trace was gone. And although I maintained a strict watch for nearly an hour, no recurrence took place." So this event, this solar flare that we now know, was very quick. By the time he had gone to get somebody and came back, it was gone. But luckily for us, he actually drew what he saw. So here is this sunspot group, and these 2 kidney bean-shaped elements, these white kidney beans, are the giant flash of light that he saw. And then he ran to go get somebody, and when he ran back, the giant flashes of light turned into C and D. They were much dimmer, practically non-noticeable, and much smaller. But unknowingly to Richard Carrington, he just made the first ever observation of a solar flare. But this was not the only weird thing that happened on this day. 16 hours later, there was what we call a ground level enhancement. And this ground level enhancement did some strange things of its own. For starters, it created these mysterious electric currents in what we call a telegraph. I think everybody calls it that. The telegraph at the time was the only form of long-distance communication. You would use Morse code to send long-distance signals to faraway places. And these electric currents were preventing these telegraphs from working. In some cases, extreme cases, telegraphs sparked. And in other cases, telegraph towers were even set on fire. And more interestingly, some were functioning without power. They unplugged them, removed the battery, and people were still able to communicate. So these telegraphs were wireless before it was cool. In addition to this telegraph peculiarity, there was also the greatest northern and southern lights event we have pretty much ever seen. This is a photo of the Aurora from the International Space Station, and the northern and southern lights are normally reserved for just the poles. You can't really see them at low latitudes, but in this instance, the aurora could be seen as far south as Texas and as far north as Australia, which is Texas of the southern hemisphere. So I'd like to tell a few stories about the ground level enhancement. First one being from a telegraph operator. This is what a telegraph office looked like at the time. And one of these men, well, not exactly, but you could assume, was the telegraph operator that we were about to talk about, named Frederick Royce in Washington. As a result of these strange currents. The other story I'd like to tell is one from Mr. C.F. Herbert, who observed the aurora for the first time. He was a gold miner working in Australia when he describes a scene of unspeakable beauty. He says, "Myself and two mates, looking out of the tent, saw a great reflection in the southern heavens. It was a sight never to be forgotten. The rationalist and pantheist saw nature in her most exquisite robes, and the superstitious and fanatical had dire forebodings, and thought it a foreshadowing of Armageddon and final dissolution." Very eloquently put, Mr. Herbert. I particularly like this quote because we all kind of assumed that maybe people were freaking out, but he tells us, yes, everybody was freaking out. I know personally I would have thought it was the end times, because back in 1859, people didn't really know what the aurora were, especially if you lived at south latitudes. You very likely didn't know somebody from up north or way down south, and so you had never heard of them, let alone seen them. And so you have millions of people for the very first time witnessing this giant light show in the sky. I could imagine you would get many different reactions. This occurred on a Thursday. I assume church on Sunday had a lot more attendees than normal. So these are all the stories I have. There's a few more stories, but I will not get into them. Very interesting. But let's talk about what actually happened. Well, this was a solar storm in two parts. The first part is a solar flare, and this is what Richard Carrington saw. As we see from this arrow, we have this active region, which is where sunspots are, and we see it's doing some strange stuff. And then the bright light is that solar flare. And here, I'll see if I can play it again. There we go. So, from what we know about solar flares, and what we know from Richard Carrington's account, we can say in no uncertain terms that what happened in 1859 is the largest solar flare we have ever recorded. Not just the first, but the biggest. This solar flare here, sorry, you didn't see that. This solar flare here was the largest solar flare we had in the last 15 years, and it didn't even come close to what happened in 1859. But, as mentioned earlier, the solar flare is just one of two parts. The other part, the more dangerous part, is the shock wave. And this is that same flare, and we see these shock waves coming from the sun, and then there's the big one. And it's not snowing in space. This is high-energy radiation saturating the telescope, and that is what is very dangerous. That's what makes up space weather, and that is what caused the ground-level enhancement. So now I'd like to look at today. Back in 1859, all they had were telegraphs. That was their only form of electronic equipment. So if you didn't work in a telegraph office, or you didn't see the aurora because you were sleeping like most people, or it was daytime, your day-to-day life completely unchanged. But nowadays, we have become very reliant on electronics and technology. So solar storms, such as the one in 1859, oh, sorry. I was like, what are you guys cheering about? What happens if a solar storm, there we go, impacts us today? Well, for starters, there would be nationwide power outages. This transformer here, as you can see, looks very rough. It was fried and melted as a result of one of these events. This particular one was in Canada, and because it failed, it caused a very large power outage in Quebec. In addition to power outages, there will be disruption of electronic communication. This might be very hard to read for people in the back, I apologize, but I'll explain it. So this image shows a satellite beaming down a message to Earth. That message reads, "The quick brown fox jumped over the lazy dog." And before a solar storm, that message was able to transmit just fine. But during said event, those in the front can see a lot of very strange symbols. This message is completely unrecognizable during one of these events. So communication, very disrupted. In addition, there will be GPS system failure as a result of this disrupted communication. You can't really find out where you are if the satellite can't tell you. And while this doesn't really matter for people getting drunk in a brewery, it does matter for, say, pilots or captains of their ship going across transoceanic journeys. There will also be mass satellite loss, which I'll get to in the next slide. And if you happen to be in space during one of these, you will suffer organ failure. In some cases, it'll take a couple of years to kill you, and if it's very acute, you'll die outright. Very scary stuff. Luckily, to my knowledge, Caleb, it hasn't happened before. You would know. So now I've made this animation that I've spent way too much time on, showing you some of what happens nowadays if a solar storm were to occur. So here we have the sun on the left, myself and the moon and a satellite down here, and some Earth orbiting satellites at Earth. So the first thing that happens in a event is the flare. There it is. Very scary. So this flare consists of mostly X-rays and ultraviolet light. That is very high energy light. And when you input a lot of energy into an atmosphere, that atmosphere heats up. The atoms start to wiggle very fast. And when an atmosphere heats up, it expands. Not to this scale, but it expands. So these Earth orbiting satellites there were in space. They were orbiting just fine, no resistances, but now they are no longer in space. They are in the atmosphere. And so they slow down when they orbit. They're running into the atmosphere. So you can see here, these do not complete their orbit, and they're gone in the most amazing meteor shower we've ever seen. But this does happen. Very recently, SpaceX launched some Starlink satellites, and they put it into very low Earth orbit, just above the atmosphere. And it was only temporary, but there was a solar flare, and that solar flare increased the size of the atmosphere, and all of these Starlink satellites re-entered Earth's atmosphere, and I don't know if they disintegrated or if they crash landed, but they're no longer with us. But again, the solar flare is not what's dangerous. What comes next is this interplanetary shock. And we see this shock, goodbye astronaut, goodbye other satellites, but hello, beautiful aurora. But as we all know, with the good comes the bad. There, again in 1859, what was just telegraphs, we now have, double-digit personal electronic devices, the results of such a solar storm today could be catastrophic. Thank you. That wasn't a great woo. It sounded like you were sad. This could cause societal collapse, if bad enough. So, what can we do about it? What mitigation risks are there to prevent the impacts of a solar storm? Well, there are actually two simple solutions, but as I put here, simple does not always mean easy. The first solution, just make all of our electronics space-proof, or space weather-proof, sorry. But based on my slide here, that costs a lot of money, almost an impractical amount of money. And so you might say, well, isn't it worth it to prevent economic collapse? Well, then you get into, we don't know how often these storms happen. Thank you. The only time we have witnessed such an event is in 1859 and no other time. Every other event since then has been much weaker. So if you are building a satellite or making an iPhone, say, this piece of electronics is only going to exist for 5 to 10 years before it's decommissioned and a new one comes out. So the people that make these hedge their bets and say, I don't think a solar storm is going to happen in the next 5 to 10 years, so I'm just not going to bother. So this solution, they have much better things to spend their money on, so very likely not going to happen anytime soon. The second solution is to simply turn off your electronics during an intense solar storm. Most electronics operate just below the current threshold, and these mysterious currents from the ground level enhancement cause it to go above that threshold where all of your electronics break. But if you just turn off your electronics, then the induced currents don't actually exceed the current threshold, and a few hours later, you can turn them back on, and it's as if nothing happened. However, there's some problems with this. One, by the time we see this bright flash that Richard Carrington saw, the damage is pretty much imminent. So we need to be able to predict when a solar storm will occur. And I know what you're thinking. Predicting the future, that's very simple, not a problem. Well, that seems to be the solution that society has chosen for us. Several countries, including our own, are actively seeking space weather forecasting capabilities that can, in fact, predict when one of these things will occur. However, we are very much not close. We have a long way to go, not doing a great job so far, but each day we seem to be making headway. So hopefully in the future, when we say, hey, everybody, turn off your electronics for the next few hours, unplug your oven, it will be because we are potentially avoiding the next doomsday scenario. Thank you very much. This is very right. Oh, that's right, I got to answer questions. Thank you.
Really interesting and a little spooky, but you know, we're close enough to Halloween that appropriate. So. All right, we'll start with questions. As a reminder to everyone, please text your questions to that number. There's a lot of questions, so I probably won't be able to get to all of them.
How do you guys have questions? I explained everything perfectly. I would say yes. This event is, generally speaking, the event we tell Congress when we are trying to say, hey, please give us money. And without this event, it would be very hard for us to know the magnitude of what these solar storms can actually reach. So I paused, but it's after the talk, so it's okay. So it would definitely look different because I don't think there would be as much of a push to try and predict space weather events. Although I think that it still may exist, but just not nearly as large scale as it currently is. Everything else would be the same, I would assume, if it has nothing to do with actual like space weather mitigation.
All right. EPM, hardened electronics better able to handle a solar storm.
EPM? Oh.
EMP.
Yes, so that is actually part of the first solution there. You can definitely build electronics to be more robust, just simple things like better hardware, thicker wires, things that can withstand this large current. And if you did that, and I don't know too much about EMP mitigated stuff, but I assume that's what they do. They are just designed to subsist electronic disturbances. And so, yes, the answer to that question, they would be better suited. But again, it costs way more money.
How much expansion in the Earth's atmosphere could be expected from average solar flare?
Average, definitely not much. If you go into the average to large range, there is a significant amount, and oftentimes what happens is a satellite will disappear. It'll go offline for a moment, and that's kind of scary because, well, we don't know where it is. And when it turns back on, we communicate it with it, and we say, hey, where are you? And it tells us, and oftentimes we have to do a slight orbital readjustment. So that is a common thing that happens. If a very large 1859 level event were to happen, you could bet that just about every single satellite would be in that state, and there would be a lot of panic going forward.
So how would a solar storm, you showed us the photo of the Canadian Quad transformer.
Yes.
Why would it only be confined to that area? Like, why was there more?
So in this instance, most solar storms don't actually get, when you look at the Aurora, they don't get as far down south as Texas. The larger a solar storm, the further down in latitude, so towards the equator, you actually get. And so in the Canadian power outage, it was a very large solar storm, but it was only large enough to really get down to Canada. So you could think of it starts in the poles, and the larger it is, the further south it can go. And so places in Canada deal with this quite frequently, but people in Texas do not.
So did anybody else besides Carrington report the event, or was it just Carrington?
That sounds like a planted question. As a matter of fact, yes, you asked that question, didn't you? Because, let me see this. No, there we go. I had an extra slide. I didn't have time to put it in, but I thought it was interesting. It has been very gratifying to me to learn that our friend, Mr. Hodgson, was a witness of what he also considered to be a very remarkable phenomenon. I have carefully avoided exchanging any information with that man. So the reason he did this was because he didn't want to spoil what he thought was very important science, and he was exactly right. He waited a couple months till there was an event. I think this was not the event. There was some Royal Astronomical Society event that they both attended, and they both, corroborated their stories. And very interestingly, in this paper, Monthly Notices of the Royal Astronomical Society, the very next journal article was Mr. Hodgson's observation. Although I don't believe Mr. Hodgson drew a picture, and thus Richard Carrington is credited for being the first one to record this observation.
Very interesting. Okay. I like that quote.
You're out of time. The computer's changing.
There's just so many questions. Oh, this one's a good one.
Uh-oh.
Well, just,
The other ones weren't good enough, guys. Sorry.
I mean,
You don't explain. It's okay. It's okay.
How long would it take for those particles, the highly energized ones at least, to reach Earth? So the time between.
That is a very good question. There is a large range. So, with that bright flash of light that Richard Carrington saw, there's also very high energetic ions and electrons moving at practically the speed of light. So they arrive with us, or with the solar flare, which is why a lot of the damage is already imminent, as mentioned. These satellites, once you see that bright flash of light, they're also in a lot of danger. But there's also a lot of slower particles. But these slower ones can still be very damaging. And most of these slower ones exist right next to that shock wave. They actually just are localized right around that shock wave. So when the shock wave passes, what's actually happening is you're just being bombarded by way more energetic particles than you had been previously. They're all localized right there. And that's what's very dangerous. And they're not that high energy, but there's enough of them that they can do some serious damage. All right. Thank you guys again. It was a pleasure.
Thank you. Thank you so much, Sam. All right, that was really, really cool. So now we move on to our break. We will take a 10-minute break, and then we will five. 5-minute break. We will reconvene and continue with our program. Be sure to check out our merchandise while you have a chance. And if you are ordering stuff from the bar, just wait here for the servers to come around. Don't crowd the bar, and tip your bartenders and servers. Thank you. Testing.
Oh, you need Vincent? All right, everybody, we're going to move along now. So we're going to have our own Caleb Gamar. He's a UTSA SWERI grad student. He's going to come up and give us some updates. Astronomy in the news. Everybody, here's Caleb.
All right, so hello everyone, and glad to be back doing astronomy news. So let's go ahead and get started. So first and foremost, what is in the sky this November? Well, if you look up there, you will actually start to find 3. Yes, count them, 3 planets up there in the sky, easily seen to the unaided eye. Of course, Jupiter and Saturn will still be up in the sky. So this is looking about 9 o'clock p.m. By the way, we do the fall backward thing time-wise this coming weekend, so do bear that in mind. So yeah, I know. So about 9 o'clock p.m., if you're looking up in the sky, this will be the sky, about mid-month, around 9 o'clock p.m. You will see Saturn setting over toward the southwest, Jupiter, just a little off center of the sky, and then Mars will be rising over toward the east, and Mars will get brighter and brighter as the month goes on, because by the end of the month, basically from November 30th heading into the early part of December, we reach very close approach with Mars, so you will have a very, very bright Mars in the sky as the month goes on. Also, do make sure, as I always say, to scan the sky, especially along that Milky Way there, with a pair of binoculars. There's a lot to see there, way more than what I can cover in this very brief moment of time with you this evening. And we do have a total lunar eclipse coming up. Now, we will not be able to see the entire eclipse from here in San Antonio, unfortunately, but we will be able to see most of it from here in San Antonio. Basically, we will miss out on the latter portion of the eclipse where the moon starts to head out of the Earth's shadow. So it will turn this nice red color in the sky. That's actually a photograph I took myself during the last eclipse that was visible this past spring here in San Antonio. So early morning of November 8th, so get up really, really early. You're talking around 3 o'clock in the morning, going on until 6 in the morning. You'll be able to see this take place. So one of the more fascinating pieces of news that I found while doing this formulation of this presentation was of a gamma ray burst observation this past month. One of the most powerful gamma ray bursts ever observed on record. Observed from a distance of about 2.5 billion light years away. Very, very far away. All right, so we're looking at that as it appeared and happened a long time ago. So this imagery right here is actually from the Fermi Large Area Telescope. That's a space-based, basically a high-energy observatory. And you actually see the gamma ray burst happening there, the very intense burst of radiation there on that sequence of images. But this was a multiple telescope observation. The Swift X-ray telescope also imaged this particular gamma ray burst. And then a follow-up observation from the Gemini South telescope was able to see the visible light signature of this, probably the collapsing of a supermassive star into a black hole. So a very, very fascinating observed event very recently. Now, there have been some very weird exoplanet discoveries announced over the past month. A couple of these, their names are WASP-76b and WASP-121b. Yeah, I know, really great names. The WASP stands for Wide Area. Wide Area. Oh, great. Anyway, yeah. Anyway, nonetheless, though, it does stand for a certain exoplanet survey. And nonetheless, so in this case, they found in the atmospheres of this exoplanet of heavy elements, which is surprising, barium. Now, in most very large gaseous planets like this, you would think that all of the heavy stuff falls into the planet and more lighter stuff stays in the outer atmosphere. But nonetheless, though, in this case, that does not appear to be happening there. There's actually heavy elements in the outer atmosphere of the gas giant. And then the other exoplanet discovery is for T, which stands for TESS Object of Interest. That's an easy one to remember. TOA-3757b. This particular gas giant planet has basically a marshmallow kind of density. So we've all heard that thing about Saturn being able to float in a bathtub if you could find a bathtub big enough to put Saturn in. Well, nonetheless, though, this particular gas giant planet, again, has a density comparable to that of a marshmallow. So there actually is a marshmallow world out there in the solar system somewhere. Yeah, you're right. Okay, so now this is a piece of news I go by with a little bit of a heavy heart, because this mission's actually ending pretty soon. InSight is actually ending. There's just not enough energy to keep keep the lander going, so it is running out of energy. But nonetheless, though, back in December, so this has been a long time ago, InSight detected a magnitude 4 Marsquake. Wow, very interesting. But they didn't know what caused a Marsquake. Well, just over the past couple of weeks, there was a series of images released from the camera aboard the Mars Reconnaissance Orbiter. Actually, 2 of the cameras aboard the Mars Reconnaissance Orbiter. One of them, HiRISE, which is responsible for that one. The other one is the actual General Survey camera on board, that showed a impact crater remnant there. So before, of course, completely clear area, and then you see the impact crater that followed afterward. So about 490-foot impact crater. That is what caused this Marsquake. So yeah, that was a very fascinating discovery released recently. Now, the James Webb Space Telescope made a very interesting observation over this past month as well. This is of the shells of gas released from a binary star system. So this is what's called a Wolf-Rayet 160, if I remember right. Didn't get the name of that on there, but nonetheless, though, we're on 40. Wolf-Rayet 140. Anyway, this star, one of the stars in the binary system, is a very, very active star, has these intense stellar winds. And these very intense stellar winds collide with the lower speed stellar winds from the main O-type star in the binary system. And as that collision happens, you have these shells of gas that are generated far away. And that was visible in these Webb images. Now, in the previous visible light images, only 2 of these shells were visible. In this Webb image, you see several of them. It's really, really a great testament to the capabilities of that space observatory. So, at closest approach, these 2 stars basically reach the Earth-Sun distance, 1 astronomical unit, about 93 million miles or so. So very, very close distance together is what they approach. And their orbit's only 8 years, so these shells are generated in 8-year increments. You can kind of read the shells as tree rings almost, being able to look back in the history of the stellar system. And I will leave with this particular set of images. They speak for themselves, the pillars of creation as taken by the James Webb Space Telescope. The left-hand side picture is from the near-infrared camera, and then the right-hand side picture, this actually kind of haunting image, is from the mid-infrared imager. So really, really beautiful imagery of that star-forming region. A few things not to miss out on. Coming up here pretty soon, there will be, of course, over the next year, so it's about actually a little over a year out from now, we will have a annular solar eclipse, one of these type, on October 14th, 2023, and we will have a total solar eclipse on April 8th, 2024, so do not miss those. Eventually, the Space Launch System will launch, supposedly the middle of this coming month, but just watch out for it. It'll eventually take place. Yeah, 3rd time I've said that. First We do have a first Friday star observing at the Curtis Von Jr. Observatory at UTSA. The weather's not looking too great for that, so it may not happen, but, just keep watch out on the CVO Facebook page. So just look that up on Facebook, Curtis Von Jr. Observatory. It's there, and you say again? There's a long story behind that. I'll tell it to you some other day. Anyway, and then this Saturday, there's a thing going on. It's not completely astronomy related, but the physics department will have a table and probably will have some physics and astronomy related activities there. Monster Mash Pumpkin Smash will be taking place. All right, yeah. We'll be taking place at the UTSA campus this coming Saturday. It's over on the East Lawn Net campus, 9 o'clock a.m. till about 1-ish, I think is how long the event runs. Because I'm part of GSPS and part of the physics department there, I'm kind of leading our effort. So we'll see how well we do. I'm hoping to win it again, but we'll see what happens. So again, a very big deal event for the campus. So, come by, take a watch if you want to. And that's it for Astronomy News. Thank you very much.
All right, so we're about to get started with the second half of our lecture talks tonight. So earlier I asked how many of you are new, but how many of you all have been here a couple times before? Let's hear it. You don't have to. It's not no classroom here. How many of you were actually here pre-pandemic? Came visit. All right, awesome. How many of you have been dying to finally see a talk given by co-founder Dr. Vincent Hugh? Excellent. So it is with immense honor that I introduce our speaker for this evening, Dr. Vincent Hugh of the Southwest Research Institute. He studies the atmosphere of giant planets, mostly Jupiter and Saturn, studying their atmospheres to tell us about how planets interact with their local environment and how they respond to seasonal changes. Most of his research is done using ground-based and space-based platforms such as radio telescopes ALMA and IRM 30 meter, or the Juno mission. How many of you have heard of the Juno mission? Awesome. That was surprisingly few people. Really? Juno mission? There you go. He is does lead calibrations on one of the Juno mission instruments, the UV instrument. He is studying Jupiter from its deep interior to its outer magnetosphere. Specifically, he studies the interaction of Jupiter's magnetic field and its atmosphere, leading to the brightest aurora in the entire solar system. He's involved in ESA's JUICE mission and NASA's Europa Clipper mission. Yeah, there we go. And in case you don't know this already about him, Dr. Vincent Hugh loves sharing the latest discoveries from our current exploration of the solar system with the public of all ages. He is involved in public outreach since 2012 in France, in the US, and in Mexico. And one of the achievements he is most proud of has been guiding children to build an entire model of the solar system in southern Mexico. Another one has been to co-found Astronomy on Tap, San Antonio. And he's a solar system ambassador and just does awesome. Even it was at a star party this past weekend and does really fantastic talks. And it is my pleasure to introduce him to give another fantastic talk to all of you tonight. Let's give it up.
All right. Good evening. So tonight I decided to talk to you about some of the research we've been doing during the pandemic. So you guys will be telling me either it's good or we're completely crazy and we were becoming nuts during the pandemic. But so, oh yeah, the drinking word is gonna be plasma torus. That's two words. So you can either do, well, someone cheated the other day and gave two words. So let's do plasma and torus. So it's double trouble. So yeah, I decided to talk about one of my favorite subjects, which are Jupiter's aurora. Because as Tracy said, Jupiter has the brightest aurora in the solar system. And Juno, the Juno mission has been capturing those auroras since 2016. So we have this great mission, a NASA mission that has been orbiting Jupiter since 2016, making headwinds in the understanding of Jupiter magnetosphere and the aurora. But tonight, actually, I'm going to talk about the specific type of aurora that are created by moon themselves. So let's rewind a little bit back in time, probably not as far back in time as the previous talk, but let's go back in 1955. That was the kind of observatory people were putting out there, highly advanced, really state-of-the-art. It consists in wires like this that you see, extended over 200 meters in this X direction. And what people were trying to actually observe was radio emission coming from space. So actually radio astronomy is one of the oldest science in astronomy because we can get those waves from the ground. They don't get blocked by the atmosphere, most of them. So what they were trying to do was actually to measure radio emission coming from this dead star, the Crab Nebula. So yeah, they were observing the Crab Nebula. But every night, they were actually measuring a signal that would raise about 4 minutes later every night. So they were very puzzled by that. So by comparing with the position of the planets, they actually discovered that Jupiter was in the field of view, was right above this field, which is actually located in near Washington, D.C. And so they deduced that they actually detected Jupiter magnetic field back in 1955. So what is Jupiter magnetic field? I was hoping Sam would talk about the magnetic field, but the magnetic field is actually a bubble that protects planets that has one from the charged particle coming either from the sun or from the interplanetary space. So it has the magnetic north, the magnetic south, and you have magnetic field line connecting the two. And it is compressed in the direction of the sun where the solar wind are coming, and extended in the anti-sun direction, which is called the magnetotail. So thanks to monitoring the radio emission, we've known that Jupiter had a huge magnetic field, and we know that because Jupiter trapped charged particles within its magnetic field. So it doesn't only protect from the sun, it also trapped charged particles. So what you see here, so this is Jupiter in radio, so you actually don't see Jupiter itself, you see the emission coming around Jupiter. You see the magnetic field line connecting the north and south magnetic pole. And what you actually see are electrons that are spiraling along the magnetic field line. So going south, north, and back and forth. And at the same time, they emit what is called synchrotron emission, which is very hard to say for me that's not a native speaker. So émission synchrotron, I'll say it in French. That works. So synchrotron emission. So that's a proof that Jupiter has a very, very strong magnetic field. So this is not recorded from the state-of-the-art 1955 observatory, but more from the VLA, the Very Large Array in New Mexico. And so we can actually watch Jupiter rotate because Jupiter has this strange thing, is that it has its magnetic field that is not aligned with its rotation axis. So you can see the rotation of the magnetic field that move all the charged trapped particle over time, over 10 hours. So Jupiter rotates in about 10-hour period. So that's a little bit more about it. So this is Jupiter with this rotation axis over here. The magnetic axis is tilted by about 10 degrees, and over one full rotation, it's going to go one side and the other. And you can see here, Jupiter display huge aurora in the north and the south that are caused by the interaction of charged particles going into the atmosphere, precipitating in the atmosphere. So those are actually aurora that you see with Juno and the Hubble Space Telescope. So another discovery came a little bit later in 1965 or 69. There's actually an influence from Jupiter's innermost moon Io, or Io, so I'll probably one time say Io and the other time say Io. So that's this moon. It influences Jupiter radio emission. When it's on the one side of the planet, you get a spike in radio emission. And when it rotates, it's on the other side of the planet, you get another spike of radio emission. So that was very puzzling. So you get radio emission when Jupiter is in what is called the eastern quadrature and western quadrature, seeing from Earth. So that was actually 1964 when someone detected that Io influences the radio emission coming from Jupiter. So that was very puzzling because, of course, this scheme is not to scale. Io is much, much smaller. Io is about the size of our own moon, and Jupiter is about 300 times the mass of our planet. So it's this tiny moon has a huge influence on Jupiter system somehow. So what the heck was going on? By the way, this is being tracked now with more state-of-the-art observatory, I would say, with the VLA in New Mexico in Socorro. And because I'm from France, I need to do a shout-out to the Nancy Decameter Array that is in the northern part of France. Pretty big facilities. All right, so what was going on with Io? So Jupiter has 4 main moons, the Galilean moon. You have Io, Europa, Ganymede, Callisto. And Io is actually not the kind of place you want to go and spend your vacation. It's actually one of the most volcanic places in the solar system. Has huge volcano, dozens of volcanoes active at any single time. It releases a huge amount of sulfur dioxide in space around Jupiter. And this sulfur dioxide then get hammered by Jupiter radiation because it's a very strong magnetic field. And what it does, so again, the volcano were discovered in '79 by the Voyager mission. And we estimated that there's 1 ton of sulfur dioxide from the volcano of Io that escapes the Io system, the planet itself, or the moon itself. And guess what? Well, this little sulfur dioxide then populates the Jupiter system, and it forms what is called the Io plasma torus. Finally, we get to that point. So let's the Io plasma torus again. So again, this tiny moon has volcano. It releases sulfur dioxide. This sulfur dioxide gets like picked up by the magnetic field. So it formed this kind of donut shape out of sulfur ion and oxygen ion, so sulfur dioxide. So that's the beauty of the Jupiter system. All right, so now let's complicate the things a little bit. This Io plasma torus, so this donut shape of material that comes from Io, it actually rotates around the planet because it is taken by the magnetic field. So it rotates like a mad donuts every 10 hours. So this plasma flow is actually hitting then, it's hitting Io, and it creates waves, a little bit like when you would put like a rock in a big stream, a big river stream. It creates waves, different kind of waves, electromagnetic waves. Those waves, as you can see, the plasma is coming this way, it's hitting the moon, and it propagates those waves along the magnetic field line. It's a little more complicated than that because the wave can actually reflect and bounce back along the edge of the donuts in a way. So that's the reason why we saw that Io has an influence in emitting radio emission, because at the very end of this line, from the wave goes this way, and when it lands on the planet, it creates this aurora that are directly linked to Io itself. You could see that a little bit like a magnetic leash connecting this emission all the way to Io. So it creates what is called the Io footprint and the Io tail that is due to the multiple reflection of the waves along the torus. So it's a beautiful system, and this is why I wanted to talk about it. So we see that in the north because the waves propagate in the north, but also in the south because it propagates all the way in the southern hemisphere. So this is what we see in the south, the aurora created by Io itself, followed by the tail behind. So Isn't it beautiful? All right, so now I'm going to introduce this plot because it's going to serve a little bit later. So if you look at the system towards the equator, so you see you see the EO itself. You're looking straight this direction. This is the equator of Jupiter. The plasma is flowing this way. It's propagating towards the northern aurora and towards the southern aurora. So over here in the north and over here in the south. All right, so if there would be only EO, that would be very simple. They actually, all the moons, or most of the moons of Jupiter have this phenomenon. All the moons interact with the donuts created by EO of charged particles. And all the moons have their own, aurora created from the interaction between the rotating donuts and the magnetic field. So if you look at the aurora, you actually not only see EO that is here seen from the side, so EO is right here, so here is the link between EO itself and the northern aurora, but you also see that for Ganymede, so here is the wave created here, propagating all the way to the northern ionosphere, the northern region, and same thing for Europa. What's up with Callisto? Well, I mean, it would be good, but people claim they detected it, but it would be good so that there's no jealous. Everybody has their own aurora. All right, so what's up with Juno? Well, we've been learning them from a remote standpoint for a long time. But now with Juno, we have the beautiful spacecraft that is actually orbiting and passing through the leash, the magnetic leash connecting the footprint, the aurora of the moon, and the moon itself. And so Juno has a lot of instrumentation that is designed to measure the electromagnetic wave that are connecting the two of them. And at the same time, you can observe those aurora themselves. And so this is what we've been doing with Juno. We actually proved, because that was not proven until we made the measurements, that this aurora created by EO is actually really caused by the multiple reflection of the wave. So that's really a big result that Juno has brought us. So now, if that would be the end of the story, that would be not be fun, because there's a little more complexity in it. So actually, there is one main aurora, but there's actually several sub-spots. Sometimes you see the main spot followed by a trail. So this is again the same scheme. This is why I introduced it before. You have EO over here. You have a plasma flowing from left to right, making waves. The waves propagate in the northern aurora, in the southern aurora. And sometimes we see that the main spot is actually preceded by a smaller spot. So that a lot of people were asking what is going on, and the theory that would explain this leading spot was caused by the wave going to the northern hemisphere, and then when it creates this aurora at the same time, it shoots some electrons the other way that goes all the way to the other hemisphere. So that would be this little subspot might be created by an electron beam going from one hemisphere to Jupiter all the way to the other hemisphere along the magnetic field line. So going from here all the way to the southern hemisphere. So the big question is, can Juno explain the multiple dance of the footprint? The fact that sometimes we see a leading spot followed by a tail, sometimes we see a main spot preceded by another spot. So the big question we've been trying to answer using Juno data is the footprint only created by the plasma flowing, creating those waves? Plasma. We need a break at this point. I promise this is the end of the story, so there's no more complexity. So the question is, can Juno explain whether those footprints are created by the plasma flowing, creating those waves north and south, creating the spot, or, as some people put together 20 years ago, created by the trans-hemispheric, the electron being going from one hemisphere to the other. So in blue you have the waves that are created, and in red this is the beam of electrons going from one hemisphere to the other. So this is where the Juno data comes in. In 2020 we were very lucky that we flew, so this is the Juno trajectory, we flew through the region connecting the moon itself and the spot, the leading spot. So this is a snapshot of Jupiter's aurora. This is a southern polar projection, so the south pole is over here. And here is the snippet of UV data that we have. So this is the main spot of Io that I showed before, the main dot with the tail. But this time we've tested the theory not on Io but on Ganymede, which has the similar kind of aurora. So here is a zoom-in version of this little region over here. And here are the spots created by Ganymede over here. 1, 2, and then maybe a third one. That's when the pandemic came. I wasn't sure that it was a third one or just the tail. And so this is when we put all the Juno data together. So I'm just going to restrict to one plot that's key to this story. So the central plot here that shows how much electron we measure with Juno as a function of time. This is the red curve that you see here. We stayed very low, kind of almost baseline, and then right here we had an increase of almost 2 orders of magnitude, so a factor of 100 of how many electrons we saw going from one hemisphere to the other, creating this leading spot over here. And so that was the one of the explanation. That was actually a nice proof that the theory of the multiple footprint is created by the beam of electron going one hemisphere to the other. And so this is a final animation that shows how complex the system is. You have the waves that are created, and the beam is created by the red spot, by the red curve. And since the whole system is rotating, well, the whole thing changes over time, and this is why we try to explain the dance of the footprints. So that's the end of the story. This is a paper we published this year, actually, and it's a pretty cool results that we got. I mean, I get very excited about that. So thank you for your attention, and if you have any questions about Jupiter and its aurora or the moons, I'm here to answer them. Thank you.
All right, thank you, Vincent. That was very, very interesting. Jupiter is one of the best systems in the solar system, so I'm not biased or anything.
No, I'm not biased too.
No. All right. A reminder to everyone, if you have any questions, please text to the number on the screen, and let's get going. So what is the cause, what do you think is the main cause for the 10-degree oscillation offset?
Oh, that's a really good question. I don't know if we know the answer at this point. Saturn has a... aliens, yeah, living on Europa, maybe. Saturn has a very axis-symmetric planet, so the magnetic field is perfectly aligned with its rotation axis to very few degrees. But on Jupiter, it's true that the offset is 10 degrees, so we don't know what causes this. So now that would be a breakthrough if I would give you the answer now. So I'm sorry, I can't do it. We don't know the answer.
So Jupiter rotates 10 hours based on passage of time on Earth. How much time passes on the surface of Jupiter during its rotation?
10 hours. But I mean, Jupiter, since it's not a solid surface, we have different reference system for Jupiter. When we say Jupiter rotates in 10 hours, we're talking about the magnetic field rotating in 10 hours. What I've showed you earlier, if I go back to this plot, yes, this is the rotation of the magnetic field is 10 hours, and so that's one of the system of longitude we have on Jupiter. This is just based on the interior of Jupiter and the rotation of the magnetic field. Of course, the clouds are moving at a different rate, and so we have different system of longitude, for people who study the meteorology, the clouds of Jupiter, because there's no solid surface. And the clouds are changing all the time, so we cannot say, hey, this cloud should be longitude 0. No, it's they're changing all the time.
Yep. So if once again, we're going to have to use hypotheticals here, but if you had a perspective like on Earth, where you were looking up at the aurora from the quote-unquote surface, so within, do we know what color they would glow at? From that perspective?
Actually, we already saw the aurora on Jupiter. I think it was either Galileo. Yeah, I think it was Galileo who had some visible camera that actually captured the aurora on Jupiter. So in the visible, I mean, because in the infrared, in the UV, I mean, we cannot see those, so we use a different color scheme, like for instance, for the UV, we use a blue color scheme because the UV is close to blue in the spectrum. But for the visible, I don't think we have. We didn't have enough good instrumentation to have different filters and say, oh, this is more blue, this is more green. Yeah, I don't know the answer exactly. Sometimes it's good not to know, because.
Cool. What will study the aurora after Juno ends?
What?
What will study the aurora after Juno is kaput?
Well, the James Webb Space Telescope in December this year is going to do a campaign designed to actually map the entire aurora and better understand, because this is a really cool place. There's so much thing going on in the aurora, and just in this tiny region, as it appears to you, you can fit about 2.5 times the size of the Earth in this giant auroral region. So James Webb is going to look at this in December this year, and the Hubble Space Telescope has been observing the aurora for over 2 decades now, and is still working. So hopefully we'll observe for a long time still. Yeah.
Let's hope. Yep. Let's. So for the emissions, the auroral emissions, are they a continuous light show or are they sporadic periodic events?
Well, that's a good question. So you can see here this kind of oval. It's hard to see because we're looking from the equator. But the same thing as Sam showed, Earth's aurora had an oval that basically don't have aurora itself on the magnetic pole, but more a certain longitude. This is why you see in Canada, sometimes the northern part of the US, those aurora. But Jupiter has the same. You have this oval that is around the magnetic pole, and this oval is constant. It's always emitting, always, all the time. And then what Jupiter has more than Earth is inside this oval, there is a crazy dynamic aurora. That's something we still don't understand. It's probably caused by the interaction with the sun, with the solar wind, but we don't know. So all the flare that we see, because Jupiter aurora has huge flares, we see them within the aurora over here. So there's some parts that are dynamics and some parts that are very static in a way.
Cool. Very different from Earth. We'll go with probably one more question here. So how fast is the reflected charged particle beam that creates the smaller signature before the main emission? Is it created faster than the main spot, or does it show up later?
Can you repeat the question?
How fast is the reflected charged particle beam that creates the smaller signature before the main emission? And then is it created faster than the main spot, or does it show up later? So I guess that's...
It's a very good question,
yeah.
And I'm going to dig into more details, I guess. So you see this, and I'm going to say it one last time, the plasma torus. The plasma is moving like this. So looking towards the planets, the plasma is flowing this way. And it takes about 8 to 15 minutes for the waves to go from Io itself all the way to the auroral region of Jupiter. And And this is at this time where it was hypothesized that there was an electron beam that was created here going all the way to the southern hemisphere. And this goes much faster. This is why it explains the leading spot, because it goes to this one before this wave had the chance to go there. So, yeah, because the wave that is created takes a little more time to travel than the electrons that are faster.
Okay, very cool. Wait, one more question. I just read one that I found interesting, so why not? Because it pertains to Europa.
Uh-huh.
And so we know that the Io volcanoes are important for the generation of this footprint. Could plumes on Europa affect such a footprint as well, or not enough?
I don't think so. So we've that's you. We've tried this. We've tried to see if there was a change in the footprint in the aurora created by Io when Io goes behind Jupiter. And when it goes behind Jupiter, the atmosphere collapses because there's no sunlight to... I mean, the Io atmosphere is a very tiny thing. So if you stop sunlight, it collapses on the planet, on the moon. And so a change in the atmosphere of the moon, because the atmosphere is very tenuous, doesn't affect this interaction. That's Juno results we had also 2 years ago. So I'm sorry for the Europa lovers, but the plumes, I mean, maybe if the plumes is really, really big.
Maybe.
Maybe.
We'll have to see. All right. Well, everyone, thank Vincent again. And we will.
All right. So how was that? You had 2 incredible talks tonight. Let's thank both of our speakers.
Woo!
Just a few announcements before we move on to the trivia portion of the evening. Just a reminder, thank you so much to the Blue Star staff. Please be sure to tip your servers. Well, let's hear it for them. Yay, Blue Star. Yeah, upcoming events. What do we have? I don't have a clicker. Oh, here it is. Ooh.
Yeah, so there's, if you guys are interested, there's an event online, because I know you guys are craving Zoom meetings at this point. So this weekend, I'll be giving an update on the Juno mission, more like general results we got and what's expected until the end of the mission in 2025. So we'll share this on the Facebook page, so if you want to log in. I know it's at 6 p.m. on a Saturday, so maybe a lot of you will be busy doing something else. But we'll share that online. So.
Cool. Oh, am I going the wrong way?
I think so. Oh.
Sorry. All right. Yeah, thanks. So we can go ahead and start with our trivia. How many of you will come around with cards and some pens and things? Yep. So we're gonna start passing those out now. Do you have a...
No, just if you need your own writing utensil, raise your hand and keep it raised until you get said writing utensil. Thank you.
We'll take a little break while we set these up. If you guys want to come up to the front, we've got some cool merch still. And you can come up and bombard our speakers with questions while they eat.
Once we get untangled.
Yeah. All right, everyone.
Does everybody have a scorecard and a pen?
Everybody-
Going once, going twice, sold. All right.
All right. As always with our trivia, cell phones are not permitted because it is all knowledge that you need to have up here. And please, please, please put down just the letter of the answer. It'll make it easier on us when grading, and we can grade them quicker and get out of here quicker. So, oh, yeah. And as usual, if you are a student in any physics capacity whatsoever, then if you are an employee in a physics capacity whatsoever, sorry. I said any physics capacity whatsoever.
You heard the man. Them's be the rules.
You better not fail then. Compete amongst yourselves. Go ahead, yeah. All right, we'll start. Question one. Question one? No. Question one. Vincent.
Let me see. Question one. There
Question
we
one.
go.
No! Okay, all right. What is the name of the telegraph operator who was electrocuted during the Great Solar Storm of 1859, like our poor Beaker over here? A. Frederick Royce, B. Richard Carrington, C. Wyatt Harris, D. Joseph Lewis, or E. Ernest Wilson? Who was electrocuted during the Great Solar Storm of 1859?
And please, just the letters.
Just a letter.
Is everybody good? All right, next question. Question two.
Vincent?
Let me see question two.
No.
We get one more every time. All right. Quite a few. Question two. The northern lights are also known as Aurora Borealis. What do we call the southern lights? Is it A, Aurora Illustris, B, Aurora Stellaris, C, Aurora Australis, did I say that? Yeah. D, Aurora Visibilis, E, Aurora Coronalis, or F, Aurora Borealis South? And these are for the aurora in the south.
Pretty picture. All right. Anybody need more time? All right. Oh, it worked. It worked. Oh, damn. Question 3. Approximately how many suns can fit between the sun and the earth? A 10, B 100, C 1,000, D 10,000, and E 100,000. And as you can see, this photo, it just felt very Texas. The planets as they would be on a football field.
It's even UTSA colors.
Oh, yeah. Go birds. Or birds up. As you can see, the Earth is a 2-point conversion away from the sun. Jupiter's first and goal at the 10. Oh my God, the flooring. Yeah, the roofing.
Rudy's roofing and flooring.
Yeah, Jupiter just made it in the red.
Anybody need more time? Going
Everybody
once. Going twice. Question 3.
No, this was
Question 4. What Galilean moon of Jupiter does not create any bright aurora? This is a memory recall. Is it A, Europa, B, Callisto, C, Io, or D, Ganymede?
We will know who was paying attention. Mwahaha.
What? What? All right. No more time.
All right. Moving on to question 5. What type of light was used to discover Jupiter's magnetic field? A, visible, B, radio, C, gamma ray, D, X-ray, or E, infrared? Which somebody must hate. It's not capitalized. Which type of light? Light, also known as electromagnetic radiation, comes in many forms. I don't know why this thing stopped pairing.
It seems to lag.
No, but it's not even. Oh, no, wait. No, I was just testing and seeing. Let's try again. I'm just wondering if we have to unplug it and plug it back in. I don't know. Because it's lighting up and everything.
All right. Any more time? No? Okay. Question 6.
Vincent.
What is the name of the first human-made spacecraft to ever orbit Jupiter? A, Juno, B, Galileo, C, Pioneer, D, Voyager, or E, Europa Clipper?
Woo.
In a minute, we're going to come and pick up the scorecards. If you could hold them up for us, please. We'd also like the pens back, please, and thank you.
Bonus.
Oh, I am so sorry. We have a bonus question. Getting ahead of myself.
Give you a little bit more. Question 6, everybody good? Anybody need more time? Nope. All right. As promised for tonight, our bonus question. Bonus. Name the Galilean moons of Jupiter in order of distance from Jupiter, starting with the closest.
We're going closest to furthest.
And love this little cute cartoon. Jupiter, this is not so much an exaggeration. Jupiter really does have a lot of moons, folks. Over 70.
Does anybody need to see a question again?
Everybody good?
Question 3.
Oh, well, that's...
You got it?
3. No, back.
Back.
Yeah. There. Thank you. There's 3. Any other questions needed? If not, start holding up your cards, and then they need 4. Are you good with 3 back there? All right, forward.
Everybody's in? Okay. And we got all the pens back. Cool.
All right, let's go through the answers for everyone here. Let's let me try one more time with this thing. No, you're good. Wait, hold on. Let me. Just the first answer. All right. All right. So the first question was about who was electrocuted during that storm, and the answer was A. Frederick Royce. He did live. So he did live. The second question, which was about the southern lights, it's the Aurora Australis. Exactly. The third question, the answer was 100. You can fit approximately 100 suns between the sun and the earth. Now you know we are 100 suns away from the earth, from the sun. Question 4. Callisto was the Galilean moon that does not create any bright aurora. Question 5. Radio was the light that was used to discover Jupiter's magnetic field. Question 6. Galileo was the name of the first human spacecraft to ever orbit Jupiter. A very important mission and some very cool science. All right, and then the next one was the bonus, and the correct answer is Io, Europa, Ganymede, and Callisto in that order. So, round of applause. All right. Now for the best part, we get to give out prizes. Woo! This is the third or fourth time in a row that this has happened, but we have a tie for third place once again. And so both teams will come up and accept their equal prizes. We have Bone Men and Space Pilgrim. Come on up. And accept your prizes. No problem. Thank you. Congratulations. And now our second place winner, which will win a Stargazing for Dummies book as one of the prizes. We don't think you're dummies. We're just helping you stargaze. The answer that the winner of second place is RRP. Nice. Congratulations. And now our top winner of the night, first prize, get this cool card game, astronomy themed card game, and that beautiful photo of what I believe is active galactic nuclei.
Yeah.
Yeah. A star of a galaxy incurring star formation. The grand prize goes to Space Rangers. Come on up. Come on up. All right, thank you everyone for coming tonight. Once again, a round of applause to our speakers and our winners. Yes. All right. Thank you, of course, to the Southwest Research Institute for their continued support. And, of course, a big thank you to Blue Star Brewing Company. Don't forget to tip your waiters and waitresses tonight. Yep. And come back. So we might have one in December. We are undecided. For sure, we'll be back in the new year. But look forward to our socials. And I believe we have a mailing list. If you would like to sign up, come see. Come up. Yes. Click on the QR code, which is on the next slide, I believe. And I want everybody, just in case we don't see you in December, to have a happy holiday season and happy Thanksgiving.